actually a couple of important announcements. I have this class test graded. I should be getting to finishing up the rest because I got two classes. You guys get the other two probably by today. Hopefully by today I'll get them all done. So if I can get them in the grade book, I'll get them. You'll see them updated by tomorrow. But if anything, today we're going to be moving into some important. We're not forgetting about the unit circle. The unit circle is still going to be important for us. What we're doing now is that we're taking the unit circle and actually placing it in a different environment. We're going to be placing it in the environment that we're going to go ahead and actually put it. We're going to graph them and put it on the Cartesian coordinate plane. And when we graph it, one of the features that happens with the unit circle is that with the unit circle, what would happen after we reach 2 pi? With the units, would the values change? No, it just kept on rotating, right? So one of the things that's going to happen is that we're going to explore the concept and where the unit circle is going to be kind of broken up. And now we're going to place them on a Cartesian coordinate plane. So it's going to look like this. And where we're going to break up the unit circle and now graph it. The thing that is not, probably the only thing that's not 100% correct about this is the fact that the values are going to be slightly different. When we break up the unit circle and I look at just one of the trigs, like let's say sine, it doesn't make a perfect half circle. But what it does have is that, did you ever notice that with the unit circle, like this y value and that y value were the same? Okay, which means that when we actually do look at a sine function, this, it's going to be symmetrical. So that's one of the important features that we're going to move into, is now when we graph them. Now, another thing that's important, that whole thing that I talk about, that a sine and cosine function, they actually, we don't, with the unit circle, we don't start repeating values until we went and hit it once, right? That means we went 2 pi. I didn't have you do this, but had I had you write the tangent values, and there might be one up here. Let's look. Let's see if we can find a tangent one on the unit circle. Right here. Okay. This is the tangent value. Y'all see these numbers on this outside right here? Okay, those are the tangent values. I had you find those manually, but had I expected you to write them down, guess what would happen? They would start repeating. Okay, look at this first value. Y'all see square root of 3 over 3? Okay, now look at it after pi. Do you see that same number show up? They would start repeating actually after pi. And that's important because that means that with the tangent function, one of the ones we're going to graph, it starts cycling after only reaching pi. So one of the things we're going to define is, I'm going to need you to write down that a cycle is the pattern in which the trig function travels in one period. And one of the things that we did, one of the beneficial items that we did is that we went ahead and looked at triangles. And we said, okay, these common triangles you work with, we use them to build our unit circle. But do you all remember that we scaled the triangles? Because originally they didn't fit inside my unit circle. So we scaled them down. And the same ability that we have to scale the triangles, we're able to make them bigger. Which means that we're able to change the lengths of the unit circle. We're able to modify we're able to modify the trig functions. So the same way that we're able to, that we studied at the beginning of these 9 weeks, how to transform functions. You remember transformations of functions in where we moved them up vertically or moved them down, stretched them, or went ahead and moved them horizontally, left and right. We're going to be able to do all the exact same things with these trig functions. We're going to be able to move them up, move them down, stretch them, move them to the left or right, affect their vertical amplitude, like the vertical stretch, and also affect their horizontal. That's the reason why we have to define periods now, because if I start messing around with their horizontal stretching and I start making them smaller, I won't need that much space because I just shrunk it, I compressed it. So the length would be smaller to complete an actual period. Or if I went ahead and stretched them out, if I made them bigger, then I would need more space to actually make a whole period, to make it go all the way across. So that's what's going to be, that's kind of what we're going into. So let's talk about what does it require for us to make a period. It requires, let's see, some people are still writing, so let me give them a little bit of time to finish. I just mentioned this verbally, but I actually want you to write it down, which talks about that with sine and cosine. Sine and cosine have a period of 2 pi. Now you see how 2 pi is written kind of far to the right? It should have been a little bit closer. And the tangent has a period of pi, which means that every time we take whatever angle, add 2 pi to it, we arrive at that same location. And at the same value. Same thing with cosine. Tangent just requires a pi, as we saw on the tangent unit circle. Now, we have different names for the translation. And when we conduct a translation, you know how the first one, the easiest one before was a k-value translation? Like if I had whatever, I added something and just moved it up. It's going to be the same, except that they're going to call it an oscillation. They're going to call the axis of oscillation. So the axis of oscillation is still easy to identify because it's the one that is adding the trig function. But it's the horizontal, it's going to be the midline though. Because see what happens is from there, once we shift it, the sine function will still operate and cycle around that midline. Now normally too, in most of our functions, they also had like a vertical stretch that was normally a number that was multiplying the function, like multiplying the variable. Like if there was a 2 in front of the x squared, that was our a. In this case, it's going to be like a 2 in front of the sine, or a 3, or whatever it is. Now, if you just use one of the regular trig functions, the default amplitude is the same one as the unit, and well, it's the unit circle length. Remember how the unit circle is the radius was 1? Well, that applies with any of these trig functions. And the frequency is actually what we refer to as what was the C value in regular translation functions, because it's the one that horizontally affects the graph. So in our case, though, oh, let me fix this a second. It just the pi got moved. So how many cycles are completed in 2 pi for sine and cosine? And for tangents, it should be for pi. So pi got moved. So we have the benefit of at least taking these transformations and translations are similar to what we're doing, just have different names. Now, I'm going to have you learn an important acronym. This you know how we use October to kind of help us with the trig functions? We're going to have something that's called, it's like oats with an F. So ops. The ops is four critical items that we need to always have in order to graph a trig function. One of them being the axis of oscillation, the other being the amplitude. It's kind of like the vertical stretch. The frequency is the amount or the length that will be needed to complete a cycle. And our starting point is our phase shift. I like to take the opportunity to point out the similarities as far as the axis of oscillation. If you notice, you see how it's adding. That was what used to be known as like the K value. If you look at the amplitude, it's multiplying. That's similar to what we did in the past as well, where that same number was the number that affected vertical stretch. The frequency, that's kind of like the C value, that was always on the outside or was multiplying the X. So that's in the same spot. And as would be the phase shift or the starting point, the S, we used to note as an H value. We normally used to start there, and we will in this case too. We used to always, it was a kind of like a habit, we started with the H to move the graph left or right first, and then we'll get into everything else. So it's not anything real new, but since we're working with Trig, we have different names for things that we worked with in the past. Now let's actually, let's see where this is. We'll give everybody a little time. Good. All right, we're going to follow a safe procedure to graphing these, and it involves these steps. To graph a circular function, you're going to start by drawing three horizontal lines, and on the midline you're going to put 9 marks. The reason why 9 is that we're really putting down 8, but since we need to also, since we're counting the 0, the first mark, then it amounts to a total of 9 once you count 0. You draw 2 cycles of the parent graph. And one of the properties is that sine and tangent start at the midline. Cosine starts at the top. And I'll explain why. Now, if cosine's negative, it will start at the bottom. And if one of the tangent or sine functions is negative, then it will first go down in the cycle. I'll explain all that as well, too. Now, something helpful thing to do is actually draw some of these steps. And what I mean is that, like in the first step that talks about drawing the three horizontal lines, you're just automatically going to draw three horizontal lines. This is like the axis of oscillation. The midline is, and the other ones are going to be for the amplitude, depending on how far I stretch this trig function up or down. The 9 tick marks typically are made by first drawing the initial, drawing the end, and then making your best guess at estimating the middle. From there, you kind of scale a middle between those two, and then from there you kind of try to put tick marks in the middle. That's how you amount to 9 tick marks. And it's just, when you do it in that fashion, it kind of just helps in trying to make it as exact proportion as you can. As you saw, I mean, it's not going to be exact, but at least you're not leaving a bunch of space at the end, or so it provides a method. Now, the interesting, one of the interesting facts about this, of why the sine and cosine started, well, actually, no, the sine and tangent start at the midline, actually comes from the unit circle. In my unit circle, my initial starting point of the unit circle, what value, what coordinate was this point there? Remember, it was 1, 0, right? Okay. Which means is this: if I had I asked you on your test yesterday, what is the sine of that line or that coordinate, what would you all tell me? Remember that sine would be the y value, which means it would be 0 by looking at it, which means that you start there. Y'all notice that? Now the tangent, isn't that y over x? So if I take the y over x of that value, wouldn't it amount to 0 as well, because it's 0 over 1? So that's the reason why that one starts at there as well. Now, the cosine of that point, what is it? 1. That's the reason why they ask you to start on top, because now for that one, the cosine, you're going to start at the very top and then work your way down. One of the features is that if your sine is, or your function becomes negative, it's going to reflect. So that means that, let me show you what I'm talking about. If I brought out a sine function like this, okay, and I applied a negative on the outside of the a value, it's going to reflect it across the x-axis. So that's why y'all wrote down there you're going to start going down instead of going up when you see a negative, because of the reflection. So let's go into some other things that once you draw the three horizontal lines and you start doing some of these items, you're also going to go ahead and actually start with the phase shift, or the starting point. You're going to first, before you write any value down, you're going to make a determination if it's going to horizontally shift left or right. So that's why you're going to start with the starting point. After that, we're going to get into figuring out the frequency. Now the frequency is going to be the most time-consuming part, because it involves not only finding the frequency, but 2 subsets. That means that you're going to find the frequency, but off the frequency, you're going to use that to determine the period, which is the first subset. Second subset is the scaling. So those are going to be under the frequency. Those 2 subsets will need to be memorized, because they're not in the OFF's acronym. They're not part of it, but they fit inside the frequency. remember that we said under the frequency we're going to do the scaling as a subset? That's going to be the next thing that's written down for the scaling scales the position. So you're going to scale along the mark. You can do that from 1/4 marks. So that's going to be the subset of the frequency. The other two values are going to be easy to find because it's going to be the oscillation and then the amplitude. Now the only thing you got to keep in mind is that you got to find your oscillation before you find your amplitude, because if you find your amplitude and then try to find your oscillation, you're going to get wrong. Well, you're going to be doing double the work. So it's the amplitude depends on the oscillation. So we normally find the oscillation first. All right, good. Okay, let's actually get into implementing one of these. So we're getting into some of the exciting parts, which is actually, let's make an example. We'll start easy. We'll start with something like just a trig function without much of the identity properties to it. So let me have you write this down. First of all, when you start with these trig functions, go ahead and start by writing down OFFs, which is the acronym because we have to find those 4 components. And then after that, we're going to go ahead and work with, what do y'all want to work with, sine or cosine function? All right, so this work with sine of x. So go ahead and write those 2 things. This is going to be our example. Now, the first important thing that you're going to have to do is take the actual trig function and break it up into OFFs format. That means that identify each part. I'm going to write it out. It's going to seem longer, and it will be, but at least it does the job of identifying OFFs. The O, the axis of oscillation, that's the number that it's added on. Since there's nothing there, that means it's an identity, meaning that it's 0. 0 is the identity for addition. This is the O in OFFs. The A is also not present, which means it's the identity for multiplication, which is 1. So in this case, 1 will be there, and this is my A. The thing that's lovely is at least it's in the same location as would be, the O and the A are in the same locations as would be translation function. Sine, the next part, the frequency, that's the letter that's in front of the F, or in front of the X. Again, being that the nothing's there, that means it's an identity of 1. So this is your F, and then lastly, we're going to have our X, and then our nothing there means that we have a 0 for a starting point. So this is our S. So we have our identification of the 4 components of OFFs. From here, we're going to go ahead and draw the 3 lines. So that's where you start. When we start sketching this, you're automatically going to go ahead and just draw the 3 lines. On your midline, go ahead and draw the 9 tick marks. So I go ahead and start at the beginning and end, middle, the middle of those two, and then after that I place a tick mark in the middle of those two as well. And they add up to 9. All right, so from here, we're going to go ahead and start with the steps of finding the starting point. Now the starting point, which is S, we identify as 0, so there's going to be no phase shift with this. So I don't have to worry about that. That helps because it makes it easier. The next part will be the frequency. Now the frequency is going to be F equal to 1, and then inside there, one of the subsets of frequency is a period. This is the first subset. To identify the period, you have to recognize that the sine function does not, it rotates a complete cycle at 2 pi, which means that you're going to use the equation 2 pi over f. It's easy to remember the 2 pi, but when you think about period, now you're going to do 2 pi over f. Now the f is 1, which means that it's going to be really just 2 pi, but I'll go ahead and write it out for you. 2 pi over 1, and from here, we'll have 2 pi as my period. So in this trig function, it just takes a 2 pi revolution in order for you to get a complete cycle. Now, because I need 2 cycles, like if you remember writing on your notes, we must graph 2 cycles. Because of that, I'm going to take my period and multiply by 2. So I'll get 4 pi. And I'm going to write on here, because I need 2 cycles, I'm going to go ahead and take my period and multiply by 2. That's the only reason why I take the opportunity to multiply by 2. Which means something important. That means that this is 0, this is 4 pi. The middle tick mark, that's 2 pi. So this is lovely so far because I have my beginning, my middle, and my end. What is still required underneath the frequency is to find the scaling. You see how I have other tick marks that are not labeled? I need to find the scaling of each one. Now that one's done easily by taking to do the last subset, which is scaling. You're going to take your period and divide it by 4. Or think about your period multiplied by 1/4. Either way. This and this equal. The important thing I want to get is that if I take 2 pi and divide it by 4, I get pi divided by 2. So I'm going to be able to fill in my tick marks because I know that each tick mark is going to have a space of pi divided by 2. What's going to be new is that you're going to be asked to add, you know how we normally, when you do it automatically when you do it on graphs, like when you scale a graph, let's say by 2s, you would do 2 and then add 2 and then put 4 and then add 2 and put 6 and those kind of things. Do you notice that you're adding every time? We're going to do the same thing, but because we're dealing with pi, I'm going to be adding, like this first tick mark is pi divided by 2. And then I'm going to add another pi divided by 2. So if I add another pi divided by 2, how much does that give me? Actually, I got pi over 4 and I got 2 pi over 4. It's actually, okay, it's actually 2 over 2 pi. It's 2 over 2 pi. And it would make sense because if you think about it, let's say I brought out the unit circle. You know how this is in the unit circle? This is pi divided by 2, right? Okay. Oops. What happens if I add another? Oh, I didn't want to get that. All right, work with me. All right. So this is pi divided by 2. And what happens if I add another one of these on here? I will end up here, wouldn't I? What value is that? Just pi. Yeah, just 1 pi, which is this. 2 divided by 2 is pi. And then what happens if I add another half pi? What value is that? Yeah, exactly, 3 pi over 2, which means that this right here is 3 pi over 2. And then if I added another one, then I would get the complete 2 pi, wouldn't it? Which is the same thing as this. I already had that one listed. Now, yeah, now we never done that before. We never, in this class, we never taken, or I don't think I've ever asked you, take 2 pi and add another half pi to it. By the easiest way to do it is convert this to a fraction, make that 4 halves pi. And then if I add another pi divided by 2, it becomes 5 halves pi, or 5 pi divided by 2. So I'm going now past the first cycle. I'm going into the second cycle. And then after that, I'll get 6 pi over 2, which is really 3 pi, because I already went over 2 pi and then another pi. And then after that, I'll go ahead and get 7 halves pi. And then eventually, I'll get the 8 halves pi, which is 4 pi. So that's the only thing that will be new in the scaling, is that now you're not gonna be adding numbers, you're gonna be adding fractions of pi. Yes. Yeah, go ahead. All right. Now let's actually, now the other two items are pretty easy to find, and they're easy because the axis of oscillation, so our next part, the oscillation, that one was just y equal to 0. Just like when we found K translations, they're very direct, so is oscillation translations. Now the amplitude, oh, okay, I misspelled that, I'm sorry. Let's fix it. Yeah, I know, right? I was like, hold on a second. I think I was thinking about y a little ahead of time. All right, I know. Now it's the amplitude though. The amplitude is going to be the value a equal to 1, which means that from the midline, from the line of oscillation, the other two horizontal lines are, you're going to take the what you found for the oscillation and add the amplitude, which means you'll get y equal to 1 as being the line on top. The line at the bottom, you take the same oscillation and you subtract the amplitude, which means that the other horizontal line will be dedicated to y equal to -1. So I'll have, so I have everything I need to graph. So that's lovely, because we're going to do the grand finale. Yeah, the grand finale is actually graphing it. Now, it's going to be easy to graph it because we have all the info. First, let's define this is 1 and -1. And then now let's talk about some common features. You know how we said this is 1, 0? And we identified that the starting point, the sign of that part is 0, which means that we start here. Okay. I'm now going to think about what is it at pi over 2. Remember, this coordinate at pi over 2 is 0, 1, right? So what is the sign of that value? What's the sign of pi over 2? It's 1, yes. Which means that that's the reason why you're going to draw your next point right up there. And when you think about the next value, which is pi, which is 1, 0, what's the sign on that one? The sign of pi is 0. So you're going to come down here. So you're going to be able to draw the first part of your trig function just off those values. And then from there, we'll find the next value by examining the unit circle, but asking yourself, what is it at 3 pi over 2? And remember, this is 0, -1, which means that at 3 pi over 2, the sign of 3 pi over 2 is -1, which means that this point is going to hit the lowest there. And then when I go back to 2 pi, the sign of that is 0. So I cycle back to the same location. So I've completed my first period. Since I need 2 cycles, I'm going to go ahead and just continue that pattern, where I'm going to go ahead and now do the same thing. I reach highest there, 0 back there, -1 here, and 0 back here. And now I have my two cycles graphed. Okay, good. All right, now there's only one other page of notes I want you to write, which is that our frequency sometimes needs to be applied properly. What I mean is that anytime you look at the C value on any of our translated functions, one of the, like when if you're given this kind of function, which is common, you're going to be commonly, well not commonly, but in some of the functions, you're just going to be given ops in this format. It becomes imperative, which means it becomes necessary. In order to identify the correct frequency, you need to, this is kind of out of place, go ahead and place it in place. You need to factor out the f from this part right here. Okay. Once you factor out that f, then this is what it should look like. Okay, hey, listen, we'll end there. Tomorrow we'll just work up two of the examples and then you'll just practice graph. Now, if you get a chance, you can pick up the homework. Take an opportunity to try them, because the more you try them, one of the benefit you get is that you learn from repetition. So if you're able to repeat it and kind of ingrain it,